Welcome back, guys. We're going to go through example one again, this time using the p-value approach. The previous video, we looked at solving it using the rejection region approach. Now we talk about the p-value approach. So make sure you've watched that video just so you know kind of the setup. I've already got a lot started here. I have the hypothesis set up. We are testing if the population mean diameter of the tires is 36 versus if it's different from that, if it's above or below 36, so not equal to 36. This is a two-sided test, not equal to. We compute the test statistic quickly. I take the sample mean given in the problem, minus the null hypothesis average, this 36, over the standard error of x bar, this 0.21. There's my test statistic. In the previous video, we took this test statistic and we looked at if it fell into the rejection region. Instead, we're going to compute the p-value from this test statistic, or the probability value. That's all that means. P is for probability value. Okay, a little background concept on the p-value method. I've copied down our test statistic that we computed above. It's a z-score. All z-scores follow the standard normal distribution with a mean equal to 0 and a standard deviation of 1. If alpha equals to 0.05, I got from the problem description, it tells us we're testing at a 5% level of significance. Because alpha is 0.05, my confidence level, therefore, is 95%. So I'm going to draw some of this up. We're dealing with, again, a normal distribution at 0. My confidence for this two-sided test is 0.95. Again, I have two sides not equal to, so this is a two-sided test. That's why I chose two sides. The leftover alpha goes on both sides. So we take alpha over 2, 0.025 is the probability under this curve, and is the probability under this curve. More specifically, alpha. Alpha is the probability. I'm going to scroll up to the beginning of this handout where there's a chart that displays type 1 errors. I'm on page 2. It's kind of a nifty matrix that shows the different types of decisions we can make when doing hypothesis testing. So let's say in reality, my null hypothesis is true. But maybe I go through my research findings, and this hypothesis test, I say that it's false. So when I've rejected HO when it's actually true, there I have made a type 1 error. And alpha is the probability of that occurring. So alpha, 5%, is our acceptable threshold for a type 1 error. We're okay if we make a type 1 error 5% of the time. Any more than that is not good. Okay, so this test statistic, I'm going to calculate the p-value from it, or its probability value. Every z-score has a probability of occurring on the normal distribution. Now I want to calculate that. I will then compare it to my level of alpha and make a conclusion about the hypothesis. I'm going to start with a new normal curve. So I want to calculate the probability associated with this, and I'm going to compare it to my alpha level. My alpha level up here is a right tail probability, so I want to calculate a right tail probability with my test statistic. To calculate a probability from a number that follows a normal distribution, we'll use Excel norm.dist. This is a right tail probability, so I'm going to 1 minus norm.dist. My test statistic, since it follows a standard normal distribution, the mean is 0, the standard deviation is 1, and I want a cumulative distribution. 0.0284. is the area, the blue area. I'm going to compare it to alpha of 0.05. I split it originally into two parts. So to make a fair comparison, I'm going to multiply my p-value by 2. So my p-value, 0.057. Now I compare it to my probability of a type 1 error. Here's our decision rule for the p-value approach. If p-value is less than alpha, reject HO. This is saying if the probability of my test statistic occurring is less than my acceptable threshold of a type 1 error occurring, that's okay, I'm going to reject HO. But in this case, it is greater than my alpha level, so we do not reject HO.